In the density estimation chapter, we talked about k-nearest neighbors as density estimation algorithm. Now, in this chapter, we're going to use kNN for classification or regression. Okay, and the kNN is an instance-based approach, which means we need all the data samples for classification. So to make decisions, we have to retrieve k-closest training examples in the feature space. Okay, so we're going to talk about the algorithm in detail, but basically we have to, in the density estimations we use kNN. In that case, we actually we have to find the neighbors, right? So likewise, for classification, we have to check the neighbors from the training samples. Okay, and that's why we need all the data samples. And it is a lazy learning approach, which means actually it is a kind of extreme case of this lazy learning. So we don't train anything here. In training phase, we don't update anything here. And in the testing, to test a new sample, then we have to calculate all the distances, everything. We have to do everything in testing. So all the computational burdens lie in the testing, not in training. Okay. So let's drive kNN first for classification. So given n samples, examples, we have to find k examples in a volume around the test point x. So far is the same as kNN in the density estimation. And then here is the difference. So let k sub I examples be from I class. Okay. So since this one is a classification, so we have some labels for training samples. So we know which one is coming from which class, okay, in the training samples. So this many samples are coming from this class, okay. And basically we have n sub I examples in that class. Again, we found k examples, and in that examples, out of k examples, we have k sub I examples in I class. Okay, then we're gonna drive these equations based on this likelihood and the prior. So this likelihood and the prior can be given based on this density estimation chapter. Okay, so we already talked about these equations in the density estimation chapter. So if you are confused with these equations, then you can go back to that chapter. Okay, so this likelihood is defined by like this, and the prior is just a simple ratio. This one is the number of samples in I class, and this is the number of all the samples. So it's just a simple ratio. Okay, then again, all the time we are interested in posterior. If the posterior is not possible, then we're interested in likelihood. Then the posterior can be calculated simply by multiplying all these equations. This likelihood is coming from this, and prior is coming from here, and P of x is given by this. So this equation is also coming from this density estimation. Okay, so just multiply all of them, and then now finally we have this equation. This derivation might be a little complicated. It looks complicated, but it's not, but it looks a little complicated, but the result is quite simple. Okay, so given this x point, what is the probability of I, class I? Then find the k neighbors and find how many samples are in that class out of k examples. That's what kNN does as a classification. So as I said, simply find the k nearest neighbors and assign x to the majority. Okay, let's say omega j x is kj of k. Okay. Then if we have class I and class j, then we can compare this posterior and this posterior. And if this one is larger than, greater than this one, then this X belongs to class I. Otherwise, it belongs to class J. Okay, so let's take a look at this example on the right side. And when the K is 3 and the green one is a new data sample, and first we have to find K neighbors, 3 neighbors when K is 3, then the closest one is this one, and then this one, and this one. So we found 3 neighbors, and then we have 2 blue samples and 1 red sample. Then this one is classified to the blue class. Okay, now if K is 5, then we have to find the 5 neighbors. Then we include more red samples. Then now this sample, the green one, will be classified into the red class because we have more reds here. Okay, so kNN is quite simple, but it works great. And again, let's summarize this kNN algorithm. So when we use kNN algorithm, we have to define some numbers or some methods. So we have to define these. First, we have to define the distance metric. So basically, we can use a simple Euclidean distance, but that's not, the only option. Sometimes we can use some Marlowe-based distance. Sometimes we can use geodesic distance, and sometimes we can use some other distance. Okay, and depending on the scenario and data type and applications. And the next, we have to define K. kNN is based on the K nearest neighbors. Okay, so K is hyperparameter. We have to give this number in advance. And the last one is a way to make a prediction. So I just in the previous slide, I just used a majority vote, right? But that's not the only way. Okay, so as in the previous slide, if we have 3 circles and 2 triangle, okay, then we have new sample around here, and the K is 5. So we include 3 circles and 2 triangles. Then in this case, if we use a majority vote, then this one will be categorized into circles. But this one is too close to these triangles and is kind of far from these circles. Then we can put different weights on these data samples. Okay, if they are close, then we can put more weight, and if they are far, even they are all neighbors, but still, we have different kind of neighbors. This one is close neighbor, and they are kind of not that close neighbors. So depending on this distance, then we can put different weights, and then based on this distance weights, then probably this one can be classified to triangle class. Okay, then simply we can use something like a Gaussian distribution, Gaussian functions. Okay, in the Gaussian distribution, we have a distance in the exponential functions. Okay, then we can use it. So, and let's say this one is a distance. Then if this one distance is 0, then we have a high weight. And if distance is far, then we can put a small weight. And if it's really, really far, I think we cannot have that kind of far distance because we are talking about the neighbors. Okay, so maybe we can have some samples around here, but this one will have a small weight. Okay, and then with the new test instance, then we have to compute the distances to all the training data samples. Okay, this is computationally expensive. Think about it. when we have like 1 million data samples, 1 million training data samples, and then we have a new sample here, then to classify this new sample, then we have to calculate the distance between this new sample to 1 million training samples. That's a lot. Okay. And we have to identify k nearest neighbors out of 1 million samples if we have 1 million training samples. And then we have to find the k closest data points to the test instance. And then we can use something like a majority vote, or we can use some different kind of voting method. And if we apply kNN to these samples, then we might have these boundaries. By the way, this boundary is just kind of, we draw this figure. This is not actual result, okay? But if you apply the kNN, then probably we can have this kind of boundaries, okay? And this boundary is also kind of imaginary boundary. When we apply kNN, then we cannot have kind of boundaries. We can classify, but we cannot see this boundary. So if we want to draw boundaries, then you have to put some imaginary points. Then you have to classify. Is this in the green class or yellow class? Is this in the yellow or green? So you have to plot lots of imaginary test samples, and based on the classification, then we can see these boundaries. Okay. And even with these complicated data samples, which means in this case, yes, probably we can have some linear lines. A couple of linear lines would be enough to classify. But in this case, the linear lines are not working here. So, but even in this case, kNN can work great. So kNN is quite simple, but it works great. And let's talk about some characteristics of it. And it is simple to implement. So based on this previous slide, okay, based on the algorithm, I think you know how to implement that, right? So first, calculate the distances between the new sample to all the training samples, and then find the nearest neighbors based on, you can apply some sorting algorithms, and then find the neighbors, and then check what kind of class is the majority of these neighbors. Then just classify. That's quite simple. And it's easy to parallelize. Okay, so instead of calculating the distance between the sample, test the sample to all the training samples step by step, we can calculate this distance in parallel. Okay, so it's easy to parallelize. And it leads to a very simple approximation of the optimal Bayes classifier. This is quite important. So optimal Bayes classifier is kind of the ideal classifier. No matter what kind of classifier you have, it cannot be better than optimal Bayes classifier. It's optimal, okay? And the kNN approaches, okay? If we have a lot of training samples, and the training samples, if we have infinitely many training samples, and then if we can calculate all the distances, if it is doable, then it is optimal classifier. Okay, but there are two problems. First, we don't have that many data samples, training samples. That's the first thing. And second, even if we have infinitely many training samples, but still we cannot calculate the distances between test sample to all the training samples. So kNN could be it will be approximations, okay? But if we increase the number of training samples, then this approximation would be close to this optimal classifier. And also, it is a kind of lazy learning. or it is a memory-based algorithm, which means, as I said, we have to memorize all the training samples. Okay, again, when we classify a new sample, then we have to calculate the distance between the training sample, test sample to all the training samples, which means still, even when we classify a new sample, then we need training samples. Okay, and the model-based learning is different. We use training samples to train this model. Okay, and then once the training is done, then we don't need training samples anymore. That's model-based algorithm or eager learning. So the model will learn a lot from these training samples, and then we don't need training samples anymore. But kNN is the opposite. We don't train that much in the training phase. Actually, there is no such a thing. Like there's no training in kNN. So pros and cons. In kNN, there's no computational cost for training. Sure. And it's easy to implement, and it converges to optimal classified. That's a good thing. But is higher computational cost for testing is the problem, right? And we need greater storage to store all the training samples. If we increase the training samples, the number of samples, then we need more memory space. And there is a curse of dimensionality, because this one is not learning. Okay, this one kNN is not learning any kind of pattern of training samples. Okay, so if we have a model, and then we have a parameter, and based on these assumptions, if we have a model, then it means we have some assumption, right? And then based on these assumptions, we try to find some patterns from the training samples. But in the kNN, we don't try to find any patterns here. We keep all the training samples. So that's why we call it lazy. It doesn't learn anything from the samples. And now let's talk about some issues in kNN, because when we have lots of data samples, training samples, then it takes a lot of time. So we want to solve this computational cost. Okay, so instead of instead of finding the exact neighbors, then we approximate. Okay, so there are a couple of approaches, and KD tree is the most popular. So let me explain the idea of this KD tree. Okay, so basically KD tree is based on the binary search tree in k-dimensional space. I think you know what this binary search tree is. Okay, so you learned this thing from data structure. Okay, good. And we have an example of KD tree. Okay, there are many ways to construct KD trees, but one of them, there are many approaches, but one of them is to randomly select an axis and use a median point on the on the axis to split. So we have lots of samples. Let's assume that these samples are too many. Then randomly, we have two axes here. So this one and this one. And randomly just choose this one. Okay, so this one. And then, and in this axis, and which one is the median point? So we find the median point. Let's say we have point here, then based on this median point, then we draw one line. Okay, so we actually constructed a tree here. Okay, so left subtree and right subtree. Okay, in the left subtree, we do the same thing. So choose an axis. Let's in this case this axis, then draw a line, and with the right subtree and do the same thing, split and keep going. So with this subtree, okay, so from root node, and this one is left subtree and this one is right subtree. In the left subtree, this one is left subtree and this one is right subtree. This one is left and right. And in the left subtree we split one more time, and right subtree we split, and here we split. So we split this space into a small subtrees. Then, so let's say we have a binary search tree like this. Then this one has some input space. This one like this. This one subspace corresponds to something like this. And when we have a new data sample, okay, then we have to find a k nearest neighbors. Then instead of calculating the distances between all pairs, between the test sample to all the training samples, then use this binary search tree. So from here, we know which axis we used to split, and we know, let's say x new sample is here. Then we know this axis is used to split, and then we actually check the value here. And we know when we split, we use some specific value here. Let's say this one is 0.5, and this one is 0.5, 0.7. Okay, sorry, 0.3, 0.7. Then since this one is 0.3, then let's go to the left subtree. And then next, we used the second axis, and then in the second axis we used 0.4 as a boundary. Then 0.7 is larger than 0.4, then we go to the right subtree, etc. And now finally we have the last a node. If this one is a leaf node, then we have a space. Then in this space, in this subspace, we have lots of samples. Okay, then in these subtrees, then we can find a neighbor. We can search the neighbors. Okay, then we don't have to calculate the distance with all these samples in these subspaces. So we can reduce a lot of computational cost. But what if this subspace is too small to have neighbors? Then we can go up, right? And then we can check this one too. But basically, within this subspace, we can find neighbors. So there are many other approaches to approximate to find the exact neighbors. Okay, that's one idea. And there are other issues in kNN. First of all, distance function is a problem. Okay, and to solve this issue, then we can use a metric learning approach, and or we can simply use feature weighting. Okay, so in the metric learning, we have in feature weighting, then we have one training sample here, and the k is the dimension of the feature. Okay, and the new point x, new test sample x, has dimensions. Okay, then each dimension has different weight. Okay, and then if we change this weight, then we can change this distance function, right? So look at this figure. And for your information, this horizontal axis goes from -2 to 2, and the vertical axis goes from 0.3 to 0.3. So basically this one is hues. In that case, if we use simple Euclidean distance, then kNN works perfectly. Okay, because this one is kind of the dominant axis when we calculate the distance. But what if this one is dominant? This one goes from minus 30 to 30, and this one goes from minus 1.5 to 2. Then when we calculate the distance, then this one is close to this one rather than this one, right? Because this one is the distance between these two is simply almost 0.5, and the distance between these two is almost 5. Okay, so it looks like this one is closer to this one, but actually this one is close to this one rather than this one. So in this case, maybe you can normalize the data samples as in the pre-processing, or if we have these kind of different scales, then you can use different weights. Okay, maybe you can check the variance, and then based on the variance, then you can use a different weight. If the variance is large, then you can put a small weight on it. So it's all connected to Gaussian distributions again. Okay. And another issue is we have to define the k in advance, and depending on this k value, then we might have underfitting or overfitting problem. If k is too small, then it is sensitive to noise data. Okay, let's say we have, in this case, we have a training sample like this. This one is blue. Okay, then when we have a new sample here, then if k is 1, then it belongs to this blue class, even though this sample is in the middle of the red class, right? So if k is too small, then it depends on the outliers. The training samples are noisy, so it will kind of overfit to training samples. Okay, if the training samples are slightly different, then classification would be different. But as we increase k, then the boundary will be really smooth, which means it will not be sensitive enough to the training sample. So there is a trade-off. Okay, always it could be underfit or it could be overfit. We have to find the proper kind of area between these two extremes. But if k is too large, then it is underfitting, and the boundary is smoother than before, and it can destroy the locality of the estimation. So if we increase k a lot, then if the actual classification boundary is like this, but if we increase the, this one is x, this one is circles, then in this case, if we increase the if we increase k, then the boundary will be something like this. It's smoother than before, and sometimes this is not what we want. But it depends on the application and it depends on the data distribution. So which value is proper k? So we don't know. So you have to try different numbers from k 3 to 11 or so. Okay. And usually we need the odd number for k to break the tie. If we have 4, then when we have 2 blue and 2 red, then how do you know how to classify this new sample? In this case, yes, if we use a different weight depending on the distance, yes, we don't, even number would be fine. Okay, but if it is based on just simply a majority vote, then we need the odd number.